Okay. First, let me thank organizer Logan Agam and Anosh for giving me the opportunity to talk. Sorry? Yeah. Okay. Okay. Today we are going to talk about complex Langevin dynamics in large N gauge theories. So basically, this is a little bit motivated title. What I am really going to talk about is complex Langevin dynamics in large N unitary matrix model. So first, let me say there will be few parts of this talk. In the first part, we'll actually discuss what is an unitary matrix model and why it is important and what is complex Langevin dynamics. And then I'll discuss how this complex Langevin dynamics can be used to study this matrix model. And many analytic results is known for unitary matrix model in 0 dimension. And I'll discuss the connection of our simulation with those numerics. Now, what is first, before going to the matrix model, let me give you some motivating idea that why we're doing this. The first thing is that often in quantum theory, in Euclidean, so if you have a bosonic theory, etc., you have a real action. But once you introduce chemical potential, you often get a complex action. So it is an interesting question that how, and these complex actions are generally difficult to simulate numerically, because they cannot be easily simulated by a maximal sampling method like Monte Carlo, etc., not trivially. And there are a lot of questions. So that is the connection that why we are at all interested in, and complex Langevin dynamics is one proposed method to numerically simulate a complex integral. And there are many questions, a lot of questions in holography. For example, the phases of R-charged black hole, which I'm not going to talk about today. But these questions, even if you take a 0 plus 1 dimensional gauge theory, a very simplistic version of n is equal to 4 superangles theory, and put some chemical potential for the bosons or fermions, the question arises that what kind of phase structure it would have. And if you can really simulate this in n is equal to 4 superangles theory or even in more complicated theory, then yeah, there are holographic theories where we know very well what are the phases of charged solutions are, and they have very intricate phase diagram like third order phase transition, etc., catastrophic holography, and one can make connection with those theories. But to start from level 0, today we'll study 0 plus 1 dimensional unitary matrix model. So, just to mention that there are few other works in complex Langevin dynamics. I won't go to the whole history because it will take all my time, but mostly recent years, Get-Arts, Erhard Siller, and many other collaborators are working on this complex Langevin dynamics. And I am not a lattice or numerical person, so I may miss somebody who is sitting in the audience. Sorry for that. And then there are works recently by Jun Nishimura and collaborators who applied this complex Langevin dynamics in large N gauge theories. Okay, so they have studied the SU3 link chain and lower dimensional bosonic model, and they try to find this 10-dimensional to 4-dimensional symmetry breaking, etc., etc. So let me start my talk now after this introduction. That what a crash course on unitary matrix model. So what is an unitary matrix model? It is an n cross n unitary matrix, and it is often called a single plaquette model. If you just take one plaquette or two lattice point and define a gauge theory there, then you get this kind of various version of this model. That is, action is equal to 8 ratio plus 8 ratio dagger. So let us just cut any introduction, etc. And assume that let's assume that we are interested in this action, which is a very simplistic 0-dimensional gauge theory. And often these matrices are taken to be SUN matrix, that is simple, that is the determinant is also 1. Now this model has been exactly solved in large N by Gross-Witten and Wadia. So how the eigenvalue distribution looks like and what are the phases? So eigenvalues of the unitary matrix lies over the unit circle. Because it is a unitary matrix, eigenvalues are e to the power I theta, so in complex plane, they lie on a unit circle. And in large N, one can solve this model exactly, and one get two phases. That is, one is called ungapped phase, and other is a gapped phase. In the ungapped phase, the eigenvalue distributions are continuous over the unit circle. And then what happens? In the gapped phase, the eigenvalue distribution cease to be continuous, a gap forms. So basically, it looks like that. So this is the ungapped phase, and this is the gapped phase of the eigenvalue distribution. Okay, and so once you change this only parameter A in the theory, so you go from ungapped phase to the gapped phase. And in the middle, there is a third order phase transition, and one can do various stuffs there, like one can zoom on the phase transition and get my plane wave to kind of integral, etc., etc. We are not going to do that, but just to mention, and one can actually calculate rigorously the 1/n corrections to this and show that there is some kind of double scaling limit near this transition. But the take-home message for our purpose is that there are two phases in the theory. One is ungapped, one is gapped, and there is a third order phase transition. And this has been solved long before. And this model, as you can see, the action is not complex. So this is not what we are interested in at the end. But you can make a little modification to this action and make this action complex. So one simplistic modification is the AB model. So just change A to B. So the coefficient of trace U and trace U dagger is different now. So ACE is not equal to ACE dagger. So this is a complex action. And the question arises that can we study this action? Now, again, by using various matrix theoric methods like resolvent, etc., one can actually solve this model analytically at large N. And I believe that nobody has exactly solved this model. Nobody has solved the finite N correction for this model, but I believe that finite N corrections can also be calculated. But today, let us concentrate on the large N part. So we can solve large N theory. So what happens is that, as this is an SUN model, there are a few things here. So in the large N, one can go to a diagonal gauge and can write the eigenvalue as a to the power a into e to the power I theta plus b into e to the power minus I theta. And there is a very well-known contribution from the measure term, that is du integral, which gives a repulsive kind of log sine square theta I minus theta j by 2 kind of interaction. And another important part here is that as you are looking at an SUN model, it is important that you put a Lagrange multiplier constraint on that equation, which gives rise to the constant that sigma theta I is equal to 0. That means the determinant of U is equal to 1. So you can solve this model. Again, going to the complex plane using various methods of resolvent, etc. You can solve the model, and you can find out, just like the previous one, you can find out what is the rho theta. I mean that what is the density function for the eigenvalues, which is given by this number. Now, this number is defined on the whole complex plane. And interestingly, this number is not positive definite on the unit circle. What it means is that although we have started with a unitary matrix model, the saddle point eigenvalues lies in the complex plane. This is not something very strange. Even if you look at a real integral, you often find, say, 1 by x square plus a square. The saddle point eigenvalues is that where the pole is e to the power something x square plus I bx or some integral. There are many examples of it. But even the integral is real, the pole, means that saddle point, that integral actually lies in the complex plane. And somehow you have to deform the contour, etc., to do that integral. So here also we are observing exactly the same phenomenon, that actually this quantity is positive on this complicated curve in the complex plane, which is r as a theta is given by that. I'll show you in a second how this curve looks like. But the basic idea is that saddle point eigenvalues has been moved out of the unit circle. Okay. And this model also I'll show in a moment, then has gapped and non-gapped phases. So I'll come to that discussion when we discuss the complex Langevin dynamics. But let us take a little break and discuss something else. Something else is that we'll discuss QTD on some compact spaces into time. The basic take home, so there is some derivation, etc. I put in this paper, put here. A lot of people have done this kind of things, like in recent years. The idea is that at the end, when this cloud settles, you actually get from a 0 plus one-dimensional QCD with fermions, fundamental fermion, you again get a matrix model, which is very similar to our AB model. A bit complicated than that. It is log 1 plus u rather than a trace u plus trace u dagger. But anyway, you get some kind of polynomial looking matrix model at the end of the day. And this matrix model again has, you can do some kind of scaling limit where you get a single level matrix model like this one. You can expand and see that first few terms matches with a simple model, and it also has a very simple phase diagram which is either gapped or ungapped. And as we change this parameter, which we get is that we first start with an ungapped phase, it goes to a gapped phase, and then it again comes back to the ungapped phase. And in this transition, both in the AB model and the other model, what happens is that one can show that this M is first 0 in the ungapped phase, then it gets some expectation value in the gapped phase, and when the model again goes to the ungapped phase, M saturates to some value. Okay. So the question we would ask is that, can we find these behaviors in various kind of lower dimensional 0 plus 1 dimensional matrix from complex Langevin dynamics by doing a simulation? So what is complex Langevin dynamics? A very brief introduction, as I don't have much time left, is that, so basically, if you have an integral like this, you complexify the variable fields, z dot is equal to minus, and define a Langevin dynamics in the complex plane. You see that if eta is equal to 0, then hopefully this dynamics would take you to the saddle point of the action. If it is 0, then dynamics hopefully, not all, is difficult to prove even if it is equal to 0, because it is a complex flow. Hopefully it will take you to the saddle point of the action. So it is, one can intuitively think that this dynamics somehow zoom in the saddle point of this action. One can see so that if eta is there, is actually calculate this integral in many cases. Although there is no concrete proof, there is some heuristic proof has been given, is that, so one can show that basically the probability distribution calculated from the action of any operator, if the operator is meromorphic, then this probability distribution, so what happens for this complex dynamics is that this complex dynamics is a dynamics in two-dimensional plane. So at the end, you are expected to get a probability distribution on this two-dimensional plane if you solve the corresponding Fokker-Planck equation. And say, let us call this probability distribution Pxy of t. The claim is that this Pxy of t, when you do the integration of an operator over that probability distribution, that actually produces the expectation value of this operator O for this original action. Okay, I'm not going to the proof of it. Now, let us show some of our results for the last 10 minutes, or maybe I'll take a little less, is that, as I have said, that for our AB model, the unitary, the saddle point actually moves away from unit circle, and one can analytically find it. So this is a demonstration of this. So this is the unit circle in the complex plane. This is the AB model with A is equal to 0.20 plus something, B is some other value. And you can see that this has been moved away from the unit circle. There is another plot, is that this is more natural model, like the model is similar to this model where A and B are both real, which generally comes from some kind of gauge theory, etc. They are also that if A is not B, the saddle point has moved away from the unit circle. And this is complex Langevin dynamics. This is just complex dynamics without any noise. And we can see that our numerical saddle point, numerical eigenvalues after with the imaginary time flow actually zoomed into the analytic solution. And this is a real complex dynamics with proper noise. We can see how these eigenvalues are the, so this is numerically, these eigenvalues, we started from the unit circle, now this has zoomed onto the analytic solution, around the analytic solution. So as I have just said, that even if A and B are not complex, this is not the case which you get from a from this gauge theory, but you can choose this thing, then also this simulation works and properly zooms around these points. Okay, and then this is the phase structure of AB model. In the whole AB plane, this is the ungapped phase, this is the gapped phase. What happens to complex Langevin dynamics, we can trace this phase boundaries analytically and also through complex Langevin dynamics, and they match exactly. And this is for this model, trace 1 plus xi log u. This is the unit circle, and this is various values of xi. As you can see that as we increase xi, the gaps open up, etc., and then the gap closes, and we again reach a kind of unit circle, as I have said. And this is the result of, red is the result of complex Langevin dynamics. Unfortunately, there is another line inside it which shows the analytic solution, which is not clearly visible here, but the take-home message is that this analytic complex Langevin dynamics can produce the analytic solution exactly here. And this is, so we have done this simulation with number of degrees of freedom 500 and 500 cross 500 matrices. And with the complex Langevin time step very small, and thermalization step is 18,000 and generation step is 2,000, with measures performed after every 100 steps. Anosh knows better than me on that. So we have done two kind of complex Langevin dynamics. One is the general Euler, Metropolis Euler algorithm, which is just a simplistic algorithm of the, just put the Langevin equation in the computer. And there are other higher order Runge-Kutta method available also. And we also tried them. The interesting point is that once you go to the higher order method, the things become much faster. And previously, I believe that people did not try this higher order method that often. And one has to take very small time steps, but we can get good matching with the analytic results with biggest time step also, like 0.0, 0.01, etc., etc. Okay, this is the plot of M, or the for the gauge theory for this thing. This is actually the fermion number one can show. Otherwise, it's just a Lagrange multiplier. And you can see that, as I have said, this is, as we plotted with log xi, this is the analytic solution. This is the n is equal to infinity is the analytic solution. And for n is equal to 500, the simulation almost exactly matched with the analytic solution. Even for n is equal to 3, interestingly, as this is a physical observable, for n is equal to 3 also you get okay result. Even from complex Langevin dynamics is not that far from it. And this is the plot of Wilson loop for this model. So as this action is complex, trace of u is not equal to trace of u dagger generally. So P is trace of u, P inverse is trace of u dagger, and they are generally different. And this is the simulation for n is equal to 3. So it's very much different from the analytic results, which is plotted here. This is, but for n is equal to 500, and also even for n is equal to 30, which hasn't been shown here, we get kind of like good match with the analytic results. So we can plot various other quantities and see the match. I won't waste your time by showing a lot of unnecessary plots. So let's just, so this is the three-dimensional, the same figure drawn in three-dimensional with all other variation of parameters, etc., and how well it matches, etc. This is the same thing with this, and this is, if you change the, I think that this is not, this is P and P inverse with some noise. This doesn't look very well. This is for n is equal to 30, I think, but once you go to a higher value of n, the matching becomes very good. And this is somehow with a model with few labels of fermions, etc. One can have some analytic solution. Is equal to n is equal to 500 plots kind of exactly matched with this. And so in complex Langevin dynamics, we need to see that in this two-dimensional plane, how the eigenvalues are distributed, if their moments are too large, if they're going too much away from the core, then this simulation generally is not good, or it's not trustable. So we can show that this, in our case, if we look at the distribution of eigenvalues of this unitary matrix in the complex plane, with noise, etc., it decays sub-exponentially, possibly. So we believe that this is not a bad simulation, and if it decays exponentially, the good thing is that you can actually meaningfully calculate higher moments from this simulation. Excess moment of x square, x cube, x to the power 4. Otherwise, you cannot do those kind of things. So now we are working in n is equal to n matrix in like 0 plus 1 dimensional bosonic gauge theory with arc charge. As I've said, that there is various interesting questions there in holography, like how the charge adds up. Suppose you take a black hole. You take two charges. The black hole energy depends on q1 square plus q2 square root. The energy, so the effective charge, is somehow the root mean square of two charges. That is not something we see in free gauge theories. Then charges just add up, rather than adding up root mean square way. So can one produce this kind of behavior from simulation, even in a simplistic setup, even in 0 plus 1 dimensional gauge theory, etc., etc. So there are many exciting new avenues. We are looking at it, and that, I guess, is the end of my talk.
Questions?
In your simulations, do you use real noise or complex noise?
We use real noise. Noise means that, of course, it's a Langevin dynamics. So the total noise has to be complex, but the real and complex part is 0.
And is it possible to see in your model what are the necessary criteria for converging into the exact probability distribution? Like what can be done?
Sorry?
So what can be done to improve the complex Langevin in your case, in your model, to go to the exact fixed points? Or can you study the fixed points of this complex Langevin, whether it goes to the exact probability distribution in the real plane?
Well, means that, sorry, I did not mean that exact probability distribution is not known. So how do you know that whether it is going to the exact probability distribution?
Can it be calculated in large n, or?
Yeah, it is converging apparently, as I have shown. But so if you take the 1 by n corrections, I haven't shown the plot, but they decay with 1 by n. So now that how do they decay? And in matrix model, actually you can calculate the 1 by n corrections. So some preliminary simulation shows that these decay actually match with the 1 by n correction. But we are not pretty sure about that yet, because you know that there are two sources of error. One is the finite n, which deviates from the analytic result, and then there are a number of Monte Carlo steps you are doing. There is some error 1 by number of root of that thing, if you assume some Gaussian. So now this thing has to be much smaller than 1 by n to see the 1 by n effects very clearly. And we haven't carefully studied that regime. But preliminary simulations show that yes, they are converging.